When we have a problem like this first one, we're not actually being asked to use all those powers individually. Notice that the base is the same in each part. 2 to the ninth, 2 to the 10th, 2 to the negative fifth. And we saw in our video of the what to watch notes that when we multiply with the same base, we can add the exponent. So this is the same as 2 to the 9 plus 10 plus negative 5. So 9 plus 10 is 19, plus a negative 5 is going to be 14. So this is 2 to the 14th. From here, you would definitely use a calculator to find out that value. Plugging it into a calculator, we see that 2 to the 14th power is 16,324. I would expect to see both of those steps of work on your paper if you're doing these problems on your own. M to the 12th times m to the negative second times m. Now, the first thing is if we realize that m is really m to the first, the problem gets a little bit easier. Remember, we're multiplying with the same base, so we're going to add the exponent. 12 plus negative 2 is 10, and 10 plus 1 is 11, so this is really equal to m to the 11th. Since this time our base is a variable and not a number, there's nowhere else we can go with this problem, so it stops there. And the next one, we're going to add our exponents again. So this is going to be a to the 14 plus negative 13. So that's a to the first. More simply, we would just write that as a. Negative 4 to the negative second times negative 4 to the positive 8th. The first thing we're asked to do is multiply by the same base and add the exponent. So negative 2 plus 8 is equal to positive 6. So this is equal to negative 4 to the 6th. Now, if you're careful about using parentheses, you would be able to plug that directly into your calculator. But you know that a negative times a negative is a positive. And so if we do that a set of 3 times to get 6 negatives, we know our answer is going to be positive. So it would be just as easy to plug 4 to the 6th into your calculator and not run the risk of having a sign issue. Plugging that in, we see that this equals 4,096. All right, now this next problem is not a typo. I wanted you to see that when we have variables, whether they're uppercase or lowercase changes what the variable actually is. A lot of times in science, you might have two different amounts that you're trying to measure, and maybe the words for those things start with the same letter, like magnitude and momentum. And if you had those two things in a problem, you might choose to represent one of them with a lowercase m and the other with an uppercase m so that you can keep track of them. So we have to assume that that's what happened here. Nobody made a mistake. They specifically made that a capital B, so we have to realize that that's a different base. So the b to the 12th and the b to the negative second will be b to the 12 plus negative 2, or that should be a negative, sorry, b to the 10th. That capital B to the third is a different variable, so it doesn't get combined. So we're going to have b to the 10th times capital B to the third, and we're going to stop there because those are not the same base. In our next problem, we have 2x squared times x to the fifth. Now, we need to realize that this 2 is only applied to the x. This 2 is a coefficient, and since we don't see any other coefficients, it'll still be the same coefficient when we get done with the problem. But x squared times x to the fifth is x to the 2 plus 5, so this is really equal to 2 times x to the 7th. In our next problem, we're applying the next rule, which is the power to a power rule, as well as the product to a power rule. Inside the parentheses, we see a product. 4 is being multiplied by x cubed. That whole thing is being squared. Now, there's a couple ways to think about this. If you did it the long way, you would say 4x cubed times 4x cubed, because that's what it means to square something. You know that 4 times 4 is 16, and that x cubed times x cubed is x to the 3 plus 3, or x to the 6th. So that's one way to get to your final answer. But we hope that you remember the power to a power rule. With the power to a power rule, we know that this is equal to 4 squared times x cubed squared. This is using both the power to a power rule and the product to a power rule. So 4 squared is 16, And when I raise a power to a power, like the 3 and being raised to the power of 2, we multiply the powers. So this is 16x to the 6th. Whether you find it the first way or find it the second way, it's okay, but you do need to be aware of all the laws of exponents. All right, in the next problem, we already know that in order of operations, raising something to a power is always the first thing we do. But here we see powers being raised to powers. So that's sort of a higher priority than a single power. So first we're going to look at this part of the problem. We know that when we raise a power to a power, we multiply the powers. So this is x to the 6 times negative 4. Notice I just rewrote the x squared because we didn't do anything with that part of the problem. This is x squared times x to the negative 24th. Now I can use a rule that we've practiced quite a bit so far. When I multiply with the same base, I add the exponents. So x to the 2 plus negative 24 is x to the negative 22nd. We need to go back to our first lesson of exponents and remember that we can't leave a negative exponent in our answer. So this means we have to take the reciprocal. So we're going to have 1 over x to the 22nd. And that's our final simplified answer. The last one in this row has a couple of different rules in it. Notice here we have a power to a power, so that should happen first. xy squared times x to the 6th, because 3 times 2 is 6. But then we also notice that there's an x, and then it's being multiplied by an x to the 6th. Remember that first x is x to the first, so this is x to the 1 plus 6 times y squared. Well, that leaves x to the 7th y squared as that final product. In the next problem, it looks very complicated, but if we take it bit by bit, it's not so bad. There's actually just the product rule here. So notice I have regular numbers, negative 5 and 9, as my coefficients. Those can be multiplied together to get negative 45. Then we see an x to the 3rd and an x to the 6th. When I have the same base, I add the exponents rule. That's x to the 3 plus 6, or x to the 9th. Next, we have y to the negative 5th and another y to the negative 5th. If we add those exponents together, we get y to the negative 10th. When we look at this, the negative coefficient is fine. There's nothing weird about that. We've had lots of negative coefficients throughout this year. But the negative exponent is not fine. It means we need to take the reciprocal. So the negative 45 x to the 9th will remain in the numerator, and the y to the 10th goes to the denominator so that we've taken the reciprocal of the y. In our next problem, we can first do 2 times 3, which is 6, x times x to the 6th, which is x to the 7th, and then y to the 5th times y squared, which is y to the negative 7th. Again, we know we can't leave a negative in the exponent, so we have to take the reciprocal, but only of that part of the problem. So this is 6x to the 7th divided by y to the 7th. 3c, 2d to the negative 3rd times 6c squared. Well, there's a 3, a 2, and a 6, each of which are just regular numbers, and the product of those is 36. Here I see a c to the 4th, and here a c to the 2nd. C to the 4 plus 2 will give me c to the 6th. And then this d to the negative 3rd doesn't have anything to combine with. However, I can't leave d to the negative 3rd as a negative exponent, so it goes to the denominator to take its reciprocal. So I end up with 36 c to the 6th, d to the 3rd in the denominator. In the next problem, this 3 is a power on all 4 parts of that product. So we're going to have 2 cubed times x to the 4th cubed times y to the 2nd cubed times z to the 6th cubed. Now, typically when you do a problem by yourself, you are not going to write so many steps. In fact, you probably won't write that step out. But this is the thinking that goes into the problem. So 2 cubed means 2 times 2 times 2, or 8. X to the 4th cubed says when I raise a power to a power, I multiply the powers. So this is x to the 12th. Same rule applies here, so we have y to the 6th, and the same rule applies there, so we have z to the 18th. There aren't any negative exponents, so that's our answer. At the bottom of the page here, we have some scientific notation. Now, you practiced with the scientific notation refresher before we started this unit, but now we're actually doing operations. If we think of this like variables instead of thinking of it like numbers, I basically have a coefficient and then a base of 10 being raised to some powers. So that gives me the option to multiply the coefficients together, 0.8 times 1.28, and then to multiply by each of these powers of 10. When we reorganize this problem, it starts to become a little bit more obvious what we should do. We're going to need to use a calculator to do 0.8 times 1.28, which gives us 1.024. Now with the powers of 10, we have 10 to the 4th times 10 to the 6th. We're multiplying with the same base, so we add the exponents to get 10 to the 10th. Since the number is 1.024 and there's already just one digit before the decimal place, our answer is already in scientific notation. Looking to the right, we're going to take the same way of regrouping the problem. In our calculators, we're going to do 3.8 times 2.37, and then that's being multiplied by 10 to the negative 6th times 10 to the negative 3rd. You'll notice that in scientific notation, they tend to use the kind of little kid time sign of the x, and they're doing that so that you won't get confused between the dot time sign and a decimal point. This is pretty much the only time you're going to see me use this type of a multiplication sign this whole year. So going to the calculator and doing 3.8 times 2.37, we get 6.636 as that product. When we see the tens, that's the same base, so we add the exponent and we get a power of negative 9. Here's another rule break. Normally, we tell you you can't leave a negative exponent. You have to take the reciprocal and move it to the denominator. Or if it was a negative exponent in the denominator, you take the reciprocal to move it to the numerator. But in scientific notation, although the negative exponent does still mean take the reciprocal, we really think about it as moving decimal places. And the whole point of scientific notation is to allow for both positive and negative exponents so that we know whether we're dealing with big numbers or small numbers. So this would be the situation where you actually can leave a negative exponent as part of your answer anytime you're writing in scientific notation. All right, 2 more scientific notations. Now on this one, this negative exponent is not part of the power of 10. Instead, it's telling us that we have to take the reciprocal of this number and then raise it to the 6th power. So let's start by writing it that way. 1 over 7.87 times 10 to the negative 1st, and then that's now going to be raised to the 6th power because it's in the denominator where it said it wants to be. Using our calculator to do 7.87 to the 6th power, we see that we have the very large number of 237,601.07. Now, that's being multiplied by 10 to the negative 6th, because when we raise a power to a power, we multiply the powers. But remember, this whole thing was in the denominator. So it's really 1 over this number. Now, the first thing I would do when I have a weird number like this is probably to go ahead and say, wait a minute, a power of negative 6 means this decimal point moves 1, 2, 3, 4, 5, 6 places. Notice we're going to need a 0 out front. So this is 1 over 0.023760007. Now, that's a little bit of a strange number. You could use the reciprocal function on your calculator. That would be one option. It's probably the best option at this point, so go ahead and do that. You're going to take the reciprocal of that number, and you're going to get approximately 42.087. Now we're supposed to express our answer in scientific notation, and that decimal point is not in the right spot. So we're going to say that this is approximately equal to 4.2087 times 10 to the 1st. Last problem. We have 9.1 times 10 to the negative 5th, and that's being raised to the negative 4th. And I'm actually going to show you a slightly different way to do the problem this time so that you can choose between the way we did the last problem and the way I'm going to do this one. If I apply this exponent to each term, I would have 9.1 to the negative 4th times 10 to the negative fifth to the negative fourth. Now on the power of 10, we know that when you raise a power to a power, you multiply the powers. So this is 10 to the 20th. In your calculator, you actually could take 9.1 and just raise it to the negative fourth power. You can also think of it as being 1 over 9.1 to the fourth, but you're basically just going to have to take the reciprocal of your answer. So if we're using a calculator anyway, we might as well use it efficiently. So go ahead and do 9.1 to the negative fourth power. You'll get approximately 1.458. So we've got to switch to an approximately symbol here because we're rounding off. That is conveniently already in scientific notation because we only have one digit before the decimal.